In this video, we're going to look at our equilibrium now in 3D. Previously, we had only been working in 2D with just our X and our Y, but now we're going to be moving into the third dimension. And it's going to work exactly the same way as it was before, where we have our sum of forces in our X direction is 0. The sum of forces in our Y direction is 0. And now we're just adding in that Z component, right? The sum of forces in our Z direction is also going to be 0, because overall, our resultant force for all of this is going to be 0. This is the whole concept of statics, that nothing is moving, or if it is, it's in constant velocity. Nothing is accelerating. And so everything is just sitting at 0. It's easiest working with Cartesian form vectors, which is why we had spent so much time on it before. So we'll go ahead and look through a couple of examples to see how this works, but it's still going to be the same steps that we had been working through before. So it's setting your coordinate system, creating your free body diagrams. Sometimes you'll be projecting things into different planes so that it's easier to find your components of things. You may have to find the vectors that you're looking for or put them in Cartesian form. Again, we may go back to using the cosine alpha, cosine beta, cosine gamma. If you may recall, cosine alpha goes with the x component, cosine beta is with the y component, and cosine gamma is with the z component. So we'll be going back to those rules that we had been using with vectors, and now just applying them in equilibrium, just setting everything equal to 0 and solving for what our forces are, or whatever our problem is asking us to solve. So let's take a look at some examples. All right, so let's take a look at a very basic example where we don't need to set the coordinate system and we don't need to draw the free body diagram because it's already done for us. We're just looking at how do we set up and solve this system of equations in equilibrium. So here I have 5 forces listed on this, right? I have F1 is coming off in green here. He is entirely in the XY plane, which we can tell because I have these little gray dash marks indicating that he is entirely sitting in the XY plane. So F1 sits in the XY plane. He has an angle of 30. Our F2 is coming straight up in the Z direction. It is entirely in the Z direction. It just goes straight upwards in the positive Z direction. F3 is in blue, and it is also only in the XY plane. It comes off in the negative X and negative Y directions at an angle of 45 degrees. And then I have 2 given forces given to me. So I have in yellow coming in the positive Y axis only, 400 Newton force, and then in the negative Z direction only, I have a 200 Newton force. What we're going to do is determine the magnitudes of F1, F2, and F3. Since we have 3 equations that we can set up, our 3 equilibrium equations, our sum of Fx is 0, sum of Fy is 0, and sum of Fz is 0, we can have 3 unknowns. We have 3 equations, we can set up 3 unknowns. This is taking us kind of back to algebra 2 maybe in high school. You would have been setting up and solving systems of equations where you have 2 unknowns and 2 equations, or 3 unknowns, 3 equations. And that's exactly all we're doing here. We're just applying those basic concepts you learned way back a few years ago in high school, maybe in college algebra, and we're just applying them here in statics. No complicated calculus or anything, just doing the basic math. So the first thing that I want to do before I really get into these equilibrium equations is I want to get everybody into Cartesian form, so that way I can see exactly what my components are of everything. So my 200 and my 400 givens, right, they're given forces, we already know their magnitudes, are luckily already entirely in their own axes, in their own planes. They don't share with anyone else. So our 400 is a positive 400, in the positive y direction. So 400 j hat. I can just write it as that. Our given 200 is in the negative z direction. So it is a negative 200 k hat. And I want to break up my force 1, force 2, and force 3 in the same way, so I can clearly see what all of these components are. So if I look at F1, I wrote him here in green. F1, if I break him down into his Cartesian components, he's entirely in the xy plane. So I would have F1 times, if I want the x component, it's in the positive x direction. That is a cosine 30, F1 cosine 30 I hat. That's our x direction, our x component. And then minus, he's going out in the negative y direction, minus F1 sine, because it is opposite the angle 30, minus F1 sine 30 j hat. And there's no z direction, it's entirely in the xy plane, so this completely describes F1. Now I can see my components, I can see what is the x portion, what is the y portion, and it's going to come in really, really in handy when we're plugging into these equilibrium equations here. Let's go ahead and look at F2 next. F2 is entirely in the positive z direction. So it's just going to be F2 k hat. No angles, no nothing, he's just entirely in the z direction. And finally, our last guy, a little more complicated, is our F3. I am going to do him in lighter blue. F3. Now we are back in the xy plane, which we know by these gray dashed lines. Sometimes you'll see them as a thin solid line. Just letting you know that that is entirely within that plane. It's not coming out at all. So in the xy plane at a 45-degree angle. So our x component is in the negative x direction. And it is going to be cosine of this 45-degree angle. So negative F3 cosine 45 I hat. That's it. That's an I hat. And now we'll look at our y component here. Our y component, again, still in the negative x direction, right? This is our positive, so this is our negative y direction. Negative F3 sine, right? Because it's opposite of the angle over here. Sine 45 j hat. So that's it. All of our angles are now broken up into their XYZ or IJK components. So it's a lot easier to kind of see where we're plugging those into our equilibrium equations. Because I can come down here to my summation, this guy here, summation of my forces in the x direction equals 0, and I can pull out my I hats from every single equation that I set up, right? So I can pull out this guy, this is an I hat, equals F1 cosine 30. I don't need the I hat because they're all going to be just x's. And then look for my next I hat. I see another one here in F3, which is negative F3 cosine 45. And that's it. That's all of my I hat components. That's all of my x components, which I just saw by looking through my broken up forces. So as we did for the components in the x direction, we'll do the same for the y and the z. So our y is going to be all of our j hat components, right? So we're going to have from our F1, we're going to take F1 sine 30. Oh, I almost missed it. He has a negative sign in front of it. The signs carry through with them. It is a negative F1 sine 30. Then we have this 400 j hat plus 400. F2 has no j hats. And then finally, minus F3 sine 45 from our F3 component. So that sets up our y equilibrium equation. And now we'll finally do our z equilibrium equation, which is all of our k hat components. So that's our -200, -200. And there was only one other k hat component, one other z component, which is plus f2. So now if I want to go through and start solving these, our z equation is basically solved for us, right? You just add 200 over to the other side. F2 equals 200 newtons, right? Easy enough. These other two will make up a system of equations exactly like we've seen all throughout 2D. It's two unknowns, two equations, and we'll go ahead and set that up. I'm going to write over here so I don't lose it. My F2 is 200 newtons. And then we'll go ahead and solve these two systems of equations. Let me make some more room here. That guy. Delete. That guy. Let's move him up. Okay, right? Because these are the equations that we need. So I'm going to go ahead and I'm going to use my fx equation to get a relationship between f1 and f3. So I can say from that f1 equals f3 times cosine 45 over cosine 30. Or when I plug that into my calculator, f1 equals, let's see, what relationship is that? It is, I have it written in square root of 2 over square root of 3, f3. But if I plug that into my calculator, what I actually want, calculator, give me cosine 45 over cosine 30. F1 equals 0.816 F3. So I can take this relationship, plug it in here, and solve for F1. Or no, sorry, not plug it into here, plug it into here. Sorry, plug it into my F1, right? So I can take this guy, I can say negative F1 sine plugging that in. Plug that in to my F1, negative 0.816 F3 times sine 30 plus 400 minus F3 sine 45 equals 0. Or you can rewrite it as, no, I don't have the rewritten form, but you know, you move the 400 over, so you get 400 equals F3 times 0.86 times sine 30 plus sine 45. And you plug that into a calculator, divide that out, 400 over all of this mess here. We plug that into our calculator. And we're going to get F3 equals 359 newtons, which we can take and plug back into this relationship over here. 0.816 times 359 gives us F1 has a magnitude of 293 newtons. And this is it. This is our answer over here. All our question asked for was, what is the magnitude of F1, F2, and F3? And we found that through these systems of equations.